well, we ended here. We were talking about the index. We ended here on Friday access mode, which is the indirect mode plus an offset. Excuse me. So this is sort of an expanded table of the table that's in your textbook. We've looked at 1, 2, 3, 4. We've looked at the first 5. We haven't looked at these yet. Okay, we will look at those in a second, but we've looked at these first 5 here. And so just as a little bit of an exercise, a little bit of practice, let's look at these instructions here and see if we can identify what addressing modes are being used in each of those instructions. Okay, so let's look at the first one here. What addressing mode are we using there? The key is the parentheses, right? When you see parentheses, that's going to mean either indirect or index, right? And since there's no offset being added to there, that would in fact be the indirect mode, right? What about the next one? Num1 is a label for a memory address. Direct? I heard direct. Anybody agree?
Yes.
Okay, I got a seconder.
Immediate.
Immediate. Okay, dissenting view. Do I have a seconder for immediate? Okay, let's look at the syntax here. Oops, let's look at the syntax here. Okay, in this particular version of addressing modes, what would we need to see for it to be immediate? We need to see that pound sign, right? So there's no pound sign there, so we know it's not immediate. So we're back to direct, right? Okay, well, absolute or direct, okay, the syntax just has a location. Okay, well, that would fit. The effective address is that location. So that would be it, right? This is a memory address. It's just a label for a memory address. So that's exactly what this is, absolute or direct. Next one. Indexed, right? Again, we got parentheses, so it's got to be indirect or index. We've got an 8 in front of it, which means that the memory address, the effective address of the operand is going to be the address that's stored in R2 plus 8. Yeah, so that would be indexed or index. Okay, now the next one is obviously immediate, right? Because of the pound sign. Again, num1 is an address. So what's the difference between this one and this one? What difference does that pound sign make? What's the actual operand that's being loaded into R1 here versus the operand that's being loaded into R2 here? Yes, sir.
The value loaded into R1 is the address, num1, and then the value loaded into R2 is the value at address num1.
So close, but other way around.
Yeah, sorry.
Right? Yeah. That's what you meant, right?
Yeah.
This here in this addressing mode, you always ask, what's the effective address of the operand? Well, the effective address of the operand is num1, which means the operand itself is the number or the value that's stored at memory address num1. Right? Here, with immediate, right here, there is no effective address per se. The operand is the value that comes after the number sign. Okay? So in this case, there is no effective address. The operand, the number, is the address num1. So in this case, it's the actual address num1 that's being put into R2. So now R2 is like a pointer. It holds a memory address. Okay? Here R1 holds the number that's stored at the memory address num1. Okay? Okay, what about the next one? That's easy, right? Just a bunch of registers. So the effective address is register R2 of one operand. The effective address of the other operand is R3, so that's the register. addressing mode. Okay, the numbers are already stored in registers and being added together. Okay, and the last one, immediate again because of the pound sign, right? In this case, 250 is, I guess it could be an address, but it's more likely it's the actual number that something's gonna be done with, right? So we're taking a number 250 and putting it into R2. Now, in most registers, or pardon me, in most processors, this would not be a load instruction. This would probably be a move instruction, right? Yes, sir?
Is it only the context that lets you know whether it's a number or an address?
Yeah. Yep. You as the programmer would have to know what it is. You'd see how it's gonna be used later on, right? If it's used in some addressing mode as an address, well then it would be an address. But if it's being added to another number and the result is then, means something, then yeah. It's the context of how that number is used later on, which will let you, if you didn't write the code, which will let you know whether it's an address or just a number. Okay, so any questions about any of those? Okay, again, this is sort of the one kind of tricky part when it comes to assembler language code. Assembly language code is actually kind of easy because the instructions are so simple. Move a number from here to here. Add this number to this number, right? The instructions are so much simpler than in a high-level language, the statements in a high-level language. It's hard to go wrong, right? It's these addressing modes which is kind of the tricky thing. Okay, yes, sir.
You mentioned that when performing the immediate syntax, the last line of code.
This one?
Yeah.
Yeah.
The pound sign is analogous to defining a constant in C++. Does that mean you can't change the value of R2 in the programming mode once you've defined it?
Oh, you can change it in R2, right. Good question. Once this 250 has been moved into R2, future instructions could change what's in R2. But because this 250 is hard-coded into the code, when this line of code executes, 250 is always put into R2, right? But after that, it could be changed.
And then secondly, what if you, for the fourth line of code, instead of using immediate, could you have used indirect as well, and would it function the same?
Could I have used indirect?
Instead of using pound sign num1, you use num1 in brackets. Just for the memory location.
Not just pull the value in that one?
Why would you not? So in that case, you would do that if num1 itself would hold a memory address.
Yeah.
Yeah, I don't think that would be disallowed. I think you would be able to do that. I don't think the assembler should complain about that. So the question was, what if instead of this pound sign here, we take the pound sign away and we put parentheses around it? That would then be the indirect mode, which means num1, which is a memory location, would be interpreted as holding an address. And then you go to that memory address, get the number that's there, and put it into R2. Yeah, I think the assembler, I don't see why that would break any rules. Any other questions? Yes, sir.
Just to follow up on that, but it would break it if there was a number or value in there rather than an address?
Well, if you would change it to the indirect mode, the assembler is going to take whatever number is stored at num1 and interpret it as an address.
Okay.
Because an address is just a number,
Yeah.
right? It's just ones and zeros.
So it's not gonna break it, it's just probably not gonna work how you intended it.
Well, unless you intended
Yeah.
it to work that way. But if you screwed up and you put brackets there when really you meant to put a pound sign there, then num1 probably doesn't hold a legitimate address. I mean, and by that I mean an address where there's actually legitimate data stored. It would be a legitimate address, it would just, the data that's there is probably meaningless if you didn't mean to do it.
Is there a situation then where it would actually break it? Like, is there anything you can put in there, I guess an instruction set?
Because this is a load instruction, all you're gonna do is take whatever is at the address that's stored in num1, if we made it indirect, and it's gonna put it into R2. You're not gonna break anything in memory. It's just the number that you just loaded into R2 probably is meaningless.
Yeah, so if we were to put into num1, like another load instruction, let's say, that would be an instance where it wouldn't work.
You would put another loaded, sorry.
Yeah, so.
So we're still talking about changing this one to indirect, right?
Yeah, these are probably pretty fringe situations, but it's more of like, is there a point which the compiler is gonna say, no, thank you, and that's sort of, if that memory, it's addressing and it's trying to interpret it as a memory location, but instead it sees, let's say, another load command in there.
Well, that other load command is just, like if num1 actually holds an instruction,
It's also gonna be a number.
it's just ones and zeros.
Yeah, that's true.
So the assembler's gonna say, oh, well, I'm supposed to treat that as a memory address, and it's ones and zeros, and it'll do that. So the assembler can't find your logical errors, right? Just like a compiler can't find your logical errors. As long as you don't break the rules of the syntax, the assembler it'll produce the machine code, right? Okay, any other questions then? Okay, so, again, please, especially for the midterm, really have a firm grasp of these different addressing modes. There's lots of coding examples in the textbook itself, and if you need practice, just look at those examples, look at an instruction and go, what addressing mode is this, right? And try to figure it out, and if you ever have any questions, you can't figure something out, just send me an email. The previous. So again, reading, please keep abreast of the reading. At the end of every slide, everything in red is sort of the new stuff. So Appendix D is the ARM processor. Okay, so all the chapters of the textbook are sort of for generic processors, and then at the end of the book, the authors have, I think, 4 appendices, and each one is for a specific processor. Okay, and the one that we're looking at is ARM. The others, another one is NIOS, which we used to have the labs in. Another one is, I think, the cold fire processor. I forget what the 4th is, okay? But Appendix D is the ARM processor. And so you need to be reading that. It's not that long, okay? And what it does is it's going to revisit all of these concepts that we're looking at, but specifically for the ARM, okay? And we'll be going over a lot of that stuff in the appendix, but I highly suggest that you read this, whenever you can. And if you're like me, the first time I looked at this, I had to read it a few times, okay? So please keep your note in Appendix D. Okay, so let's move on to lecture slides 5, where we're gonna look at a few more addressing modes, and then we're gonna look at what we call directives, and then what we call basic. Thank you. Okay, so that's the absolute, or what we call the direct. Okay, so those are sort of the two out of the 3 basic ones. The number can live in a register, the number can live at a memory address, or in the third case is what we call the immediate, is the number actually lives in the instruction itself. Okay, so the operand here that we're thinking about is the number 200, and it's not in its own memory address, it's not in a register. It actually is in a memory address. It's in the memory address that contains this instruction. Because remember, every instruction also lives in the main memory unit somewhere, okay? So in this type of addressing mode, the operand we're dealing with is actually part of the 32 bits that make up this instruction. And those 32 bits live at a memory address somewhere, okay? Okay, so those are the 3 basic types. It's in an operand, it's in a memory, its very own memory location, or it's in the memory location that houses this instruction or stores this instruction itself. In the immediate mode, because this immediate operand has to be part of the 32 bits that make up this instruction, obviously this number can't be as big as an operand that is stored in a 32-bit memory location itself or in a 32-bit register, right? In this type of instruction, it consists of 32 bits. Some of those bits have to be reserved for what type of operation is being done, what this register is, its name, and then the rest of the bits can be assigned to immediate operand, but it's going to be less than 32 bits. So these numbers cannot be as big as numbers that are stored in their own memory address where they can use the full 32 bits for the number, or in a register where the full 32 bits of that register can be used for the operand. Okay, so those are the look at I/O. So this is the basic types. And then we talked about the indirect mode, which is the one that sort of, can be a little bit difficult to wrap your mind around. And that's pointers, right? So in this case, the effective address is stored in a register. That's typically how the indirect mode works, okay? So for a lot of processors, not the ARM, as we'll see in a little bit, but for a lot of processors, that's designated by parentheses, okay? If I took these parentheses away, well, then that wouldn't be a good example because you wouldn't have a load instruction there. So I won't say that. But these parentheses say that the effective address for the operand that is going to be loaded into register R2, that address is in register R5. Not the number itself that's being loaded into R2, but the memory address where that number lives. Okay, so just like we said back in 177 in C++, a pointer is a variable that holds a memory address. Same thing here. In the indirect addressing mode, this register R5 contains a memory address. And what this instruction will do, will go to that memory address, get the number that's stored there, and put it into R2. Okay, so that's the indirect mode, and we looked at this last day. Okay, back just a review that we just looked. I'm going to look at a few others well, let's look at this one too, because I think we talked about the index mode. Yeah, we did. The index mode is similar to the indirect mode, but in this case, it's just sort of an add-on. We can add an offset to the address that's stored in R5. Okay, so it's like the indirect mode, but with the addition of we can change what the address, we can change the effective address of the operand by adding a number, an immediate number here, to the address that's already stored in R5. Okay, and then that new address is where the number is stored that gets loaded into R2. Now when you do that, like this, that does not change the contents of Ri. Okay? The contents, the memory address of Ri stays the same in this particular version of this index mode. Okay? There's others where it will change, as we'll see later on when we look at the ARM, but in this basic type of indexing mode, Ri does not change. Its value does not change. The address in Ri does not change. All that happens is when this instruction is executed, that address is taken, 20 is added to it, and that address is then used as the effective address. The number stored there gets put into R2. Okay, so this becomes very handy as we'll see when we're dealing with basically arrays in assembly language programming. Okay, where we have to step from one value in memory to the next value in memory. All we have to do is change this offset. Okay, we usually call this the base address, the address that's stored in R5. An example like of that in a second. Okay, so those are the basic types we looked at. There's a few more. Pretty much every what we call RISC computer, and a RISC computer is a reduced instruction set computer. Okay, again, a RISC computer typically has the characteristics or attributes that the instructions are a fixed length, for instance, always 32 bits. Okay, and they're typically what we call a load store architecture, which means you have to use load and store instructions to get numbers from memory to bring them into registers into the CPU. And once they're in registers in the CPU, then the add and subtract, multiply kind of instructions can be used to operate on those numbers. Okay, a CISC computer, a complex instruction set computer, typically is the instructions can be different lengths in bits. They can also be multiple words or not. Okay, so the instructions are a little bit different. They're a little bit more complex. So sometimes your CISC code is a little shorter. You need fewer instructions to do the same task because the instructions themselves can be more complex, okay? All the RISC computers will have the addressing modes we just looked at. The CISC type of computers will also have some additional modes that we'll look at in a second. And some processors, like the ARM, are kind of a combination of both, okay? And we'll talk about that more in the next slide deck. Okay, so let's so those were the 5 basic, and yeah, we're gonna look at what we've looked at. So let's look at an example of how we would use, for instance, the indexing address mode, right? Which is the indirect plus an offset. And so in a lot of applications, we use arrays in high-level programming languages, right? When we have a lot of data that we want to organize. And we can do the same thing in assembly language program. This is the common visual that we use for memory, right? So these are individual memory locations. These would be their addresses or the labels that correspond to the addresses of these memory words. And these, for instance, could be, like in the ARM, these would be 32 bits, 4 bytes of 8 bits, right, each. And so maybe in this particular application, we want to write some code where we're going to, I think in this case, we're going to add up all the test scores for a student, okay? So we've got a bunch of data, we've got a bunch of students, looks like small n students, and there are 4 entries for every student, the student ID number, and then their result on 3 tests, okay? So an array, even in C++ or any other high language program, we like to think of 2-dimensional arrays as being matrices, right? A computer doesn't store it that way. It just stores things in sequential order in memory, okay? When we think of a multi-dimensional array, that's just for us to visualize. Computers just store it one value after another in consecutive memory addresses, okay? So the data could be stored in memory like this. The student ID number, or the first actual memory word is the number of students, okay? We have to know how many students, so that's stored in this first memory location. And then the student ID number for the first student, her results in 3 tests, and then student number 2's ID results for 3 tests over and over and over again, okay? So let's imagine that that's how our data is organized in memory. And what we want to do, we want to sum the scores, I see, for each test over all students. So maybe I want to compute the average for test number 1, which means the first thing I have to do is I have to add up all the test number 1 results over all the students, okay? So that's what we want to do in this case. So here's the same memory map. These are some assembly code that would do this, okay? And again, this is just a generic processor. So we're familiar with a lot of these instructions already, okay? And again, sometimes, just like in C++, it's good to sort of keep track of what's in everything. And I typically run out of room, so let's start down here. The first instruction is a move instruction. So that means we're going to move a number from one place to another place, okay? We are using, in this case, the immediate addressing mode, which means there is no effective address. The actual operand is list. And list is a memory address, okay? It's a label that corresponds to a particular address in memory. So this address list is going to be moved into R2. So R2 contains list. The next 3 instructions are just going to write zeros into those 3 registers, R3, R5, R3, R4, and R5. Okay, that's all the clear instruction does. It just writes zeros to those registers. Okay, the next one is a load. Okay, in a RISC-style processor, which is obviously what this one is, a load instruction gets a number from memory and puts it into a register in the CPU. So in this case, we're going to load what's at address n and put it into R6. So what kind of addressing mode is this? This is the absolute or direct, right? The effective address of the operand is the memory address n. N is a memory address, so whatever value is stored there, which is small n, which is the number of students, is going to be put into R6. So R6 now has small n in it. So far, so good? Okay, simple instructions. They only do one thing at a time. Okay, now we're going to enter a loop. This is a label that will talk about in a second. Another load. So in this case, we're using the index mode, okay? So the parentheses means R2 is a pointer. Think of it as a pointer, so it holds a memory address, right? R2, we put list in there before. That's a memory address. We're going to add 4 to it. That's the new effective address. We're going to go to that address. We're going to take the number that's there, and we're going to put it into R7. Okay? So list plus 4. List plus 4 is this memory address, which is test 1 of the first student. We're going to put that into R7. Test 1, and I'll just put a subscript for the first student. Okay? That does not change the value of R2. R2 still has the memory address list in it. Now, why did we add 4 here? To go to the next memory word. Because we assume this is byte addressable memory. A byte is 8 bits. So that means every 8 bits in memory has a unique address, right? 1, 2, 3, 4, 5, 6, 7. But these memory words have 32 bits in them, okay? 4 bytes. So that means the address for N here is capital N. The address for the next word, which is 4 bytes later, has to be list, or pardon me, let's go with list. List is the address for this memory location. The address for the next memory location is 4 bytes later, so it's list plus 4. Okay? If these were 64 bits each, well then this would be list plus 8, this next one, right? 8 bytes later. 8 times 8 is 64. Yes, sir?
So you can only increment by the number of bytes in a word?
We want to in this case because we want to go to the next word in memory. Now in other situations, we're going to look at an example a little bit later on where the data is actually characters that were typed on a keyboard, and a character only requires 8 bits to be stored. So in a memory word that consists of 32 bits, we could store 4 characters, 8 bits each, and then we might want to go from one character to the next, in which case we would only increment by 1.
So the question would have to be explicitly provided the number of bits.
Oh yeah, it would be obvious, yeah. Okay, but in this case, we just want to go to the next memory location, and since memory locations are 4 bytes each, and each byte in memory has a unique address, we want to go 4 addresses ahead to get to the next memory word. That's why we add 4 here, and why we add 8 and 12 and 16, because list here is always this address. So to get the next address, it's list plus 4. To get the next one, it's list plus 8, list plus 12, list plus 16. Okay? Okay, so now we just entered the test 1 score for the first student. We put it into R7, okay? And again, that does not change what R2 has in it. R2 still has this list address, okay? Then we're going to add the value in R7. This is the register mode, addressing mode, right? It's all registers. We're going to add what's in R7 to R3 and put it into R3. Test 1 plus 0, put it into R3. Test 1, sub 1. Okay, then we're going to load into R7 what's at the memory address in R2 plus 8. Well, R2 still has list in it. List plus 8 is test 2. Okay, so now test 2 is going to be loaded into R7. Excuse me, so that overwrites this. So we're doing something different than what this says up here, aren't we? I think this is wrong. Okay, so we're right here. So we're going to load into R7. What's at R2 plus 8? R2 has list in it. List plus 8 is here, so we're going to add this test, or we're going to load that into R7. And then we have another add where we're going to add it to R4. Oh no, we are doing it. We put it in a different register. So now R4 gets test 2. Okay, because it had 0 in it, we add 0 to what's in R7, which is test 2, and we put the result into R4. Okay, it's very typical in most instruction sets that, like in an add command, the two things you're adding are the far far right-hand side two registers, and the result goes into the register to the left, right? It's kind of like, high-level programming, right, where we would write an assignment statement like this. Right, same thing. The two things you're adding are on the right-hand side, and on the left-hand side is where the result goes, okay? Okay, so let's keep going. We're gonna load what is at R2 plus 12. R2 still has this list address here. Plus 12 is test 3, and we're gonna load that again into R7. So R7 gets overwritten with test 3, first student. And then we are going to add that to what's in R5, which is currently 0, and put the result into R5. So R5 has test 3, student 1. Okay, and then we're going to add, now we're using the immediate addressing mode because of the pound sign, so we're gonna add 16 to what's in R2. Well, R2 is the address list, okay, so list plus 16 is this address now. Okay, and we put that back into R2, so R2 now gets overwritten with list plus 16. Okay, so now we're looking at the next student in our array. We are then going to subtract the immediate value 1 from what's in R6. Well, R6 has n, so if there's like 10 students, this would be 10. We're going to subtract 1 from 10 and put it back into R6, so this becomes n minus 1. That's our counter. So we've decremented our counter. Now we've got a branch instruction. Branch if the contents of R6 is greater than 0. Yes, this is presumably, you know, if n was 10, well, this is now 9. That's greater than 0. This is true. So we're going to branch to the label loop, which is up here. And we're going to go through this whole thing again, this time adding this test 1, this test 1 to this register, this test 2 to this register, this test 3 to this register. Okay, because now R2 has this address in it, and so this first load instruction is going to add 4 to that, which is this one here. Load it in, add it to R3. Then it's going to load list plus 16 plus 8. Okay, that's this memory address here, 16 plus 4, 16 plus 8, right here. Okay, so it's just going to add up all the test 1s in R3, all the test 4s in R2, all the test 2s in R4, all the test 3s in R5. And it's going to keep looping like this until our counter here, which is R6, finally hits 0. Okay, then it's not, when it hits this branch, this will be false, so instead of looping back here, it's just going to go on with the next instruction, which is a store instruction. So store says, take whatever's at R3 and put it in the address sum1. Okay? Sum1 is presumably another, somewhere here in memory, we've got an address sum1. Okay, so whatever is in R3, which is the sum of all the test 1s, is going to be stored here in this memory location sum. Same thing with R4 is going to be stored at some other location called sum2 in memory, and R5, which is the sum of all the test 3s, is going to be stored into a third memory location called sum3. Okay? So if you were writing this in C, you would use a for loop, right? You'd use a for loop. And you'd probably have a two-dimensional array where, you know, maybe the columns are students and the rows are student ID, test 1, test 2, test 3. And you probably have just a for loop where you're adding those all up, okay? This is the assembler language that would do the same thing. So when you write code in C, you write that for loop in C++, and you compile it. Well, part of that compilation process is generating this assembly language first, right? So compilation, if you'll remember, there's a number of things that happen. The first thing is to turn your C++ code into assembly language like this. So that's part of what the compiler does. And then within the compiler, there's another piece of code called the assembler, which will then turn this into 1s and 0s that get stored into memory. And those patterns of 1s and 0s correspond to all of these instructions. Okay? Any question about that code? Okay, so the only way to learn this is, you know, you're not gonna be writing this stuff on a computer, so you're just sort of doing it on paper. Do exactly what we did here, work through it one instruction at a time, keeping track of what's stored where, and make sure that it makes sense to you, okay? Any questions? Okay, if we go back to this code, right, while the processor is executing this move instruction, the program counter holds the address for this instruction, right? Because remember, all of these instructions are just ones and zeros, and they're stored somewhere in the memory unit of the computer, right? And the computer just goes through them one at a time. It always follows the program counter. When it's done the move instruction, the CPU goes, it looks at the program counter and says, oh, okay, I go to that address in memory, and I get this instruction, and I execute it. Okay? Yes, sir?
Does that mean that there's always a program counter? There's always gonna be a program counter?
Yeah.
It's necessary part.
I've never heard of a processor that doesn't have a program counter, right? Because every processor has to know where to go next when it's done its current instruction. Because remember, despite what the Terminator movies tell us, computers are not as intelligent as we are, right? We can look and we know where to go next, right? A computer doesn't have that same understanding. It can only do one thing at a time, right? So it can't remember using neurons where it goes next. It has to store that number, that address somewhere. And when it's finished doing this, okay, I go here, that's where I go next. Okay, I go to that address, I do that instruction, I'm done that, where do I go? I go there, okay? So pretty much every computer has a program counter. They might call it something else, but. Okay, where we had to, we always had to add, no, where? Here. We had to increment the pointer, right? We had to manually do it with our own instruction. So I said there was a few other indexing modes or addressing modes we haven't looked at. There is a variation on the index mode. Remember, the index mode is the indirect mode where you have a register containing an address in it and you add an offset. Well, instead of that offset being an immediate operand in the instruction, the offset could also be in another register. Okay, so you might have a load instruction where you're going and getting a number from memory and writing it into a register in the CPU, and the effective address for that number in memory could be the address in one register plus an offset in another register. Okay, so that's all we mean by this. So you'll see that with, often it'll be done in this way, okay? Or it can be a combination of this and an immediate offset where the effective address of your operand is, say, a base address in RI plus an offset in another register plus yet another offset that's an immediate offset in the instruction itself. Okay, so it just gives you a little bit more flexibility for jumping around in memory to get numbers, okay? Okay, so those are a couple. So back here mode, different variations. Another one that's used, which again is kind of a variation of the indirect. You'll notice that, the syntax, we have these parentheses again. Rather than just a general purpose register holding an address, we can use the program counter. Remember what the program counter is, right? It's also a register in the CPU, but it's a special register. Anybody remember what the program counter holds?
The next instruction?
Not the next instruction, but it's address, right? It's address, right? The program counter always holds the address of the next instruction to be executed. So if we go back to this code, in the relative address mode, the effective address of the operand is the address of the next instruction to be executed plus some offset. Okay, and you might think, well, why would we ever want to do that? Well, this is a way actually of getting around the problem with using immediate operands that have to be less than 32 bits, and some memory addresses are much bigger than 32 bits. Okay, so one way we get around that is using this where I'm getting ahead of myself, but often these are used in what we call pseudo instructions. So you might write an assembly language you might write a instruction like that when you write your code, which means take the memory address LOC and put it into register R2. This is an immediate instruction, immediate addressing mode, right? Remember, this instruction has to fit in 32 bits, 0 to 31, okay? Some of those bits, I don't know, maybe 4 of them, have to be reserved for a unique pattern that corresponds to the move instruction, right? Maybe another, depending on how many general purpose registers you have, maybe 4 bits are reserved for R2. Okay, so 4 bits, which means the rest here for LOC is 32 minus 8, 24 bits. Okay? We're looking, this is what we call encoding an instruction, right? The instruction is stored somewhere in memory in a word 32 bits long, right? So all of this information has to fit in that 32 bits. Turns out maybe we only have 24 bits left for LOC, okay? Well, memory addresses can be huge because our memories are huge now. We have so many locations in a memory unit, so that means the addresses get really, really long, okay? Maybe bigger than 24 bits. So how do you fit, for instance, a 64-bit address into 24 bits? Well, the answer is you can't. Okay, so what the assembler will do, it'll allow you to write this, but it'll actually implement it using this type of addressing function, where what you actually store in the 32 bits is not the absolute address LOC, but maybe the offset X, right? Which you need to add to the program counter to get this memory address LOC. Okay, so that's a little trick that they do, and you'll read about that when you start reading Appendix D, they talk about that as well. Okay, so you'll see it again there. So that's often where you want to use this, okay, but sometimes you can use it to yourself, but often the assembler, when you write this, it'll actually use this instead, okay? Because it recognizes it can't do this. Okay, so that's what we call the relative addressing mode. We're almost done for today. It'll do it every time you access. Time goes fast. Okay, auto increment and auto decrement. This is kind of like what we had in C++2, where you have a variable with plus plus after it or minus minus in front of it. Okay, it's kind of similar to that. A lot of times you want to your data is in sequential order in the memory, and as you're processing this data, you want to go from one address to the next, right? So there's a lot of times where we want to do that, so they built an auto increment mode where it's like the indirect mode, so register RI holds an address, okay? So in this case, the effective address will be the contents of RI. RI has an address, and that's the address you use, and then as soon as you've accessed that memory location and gotten the number out of it, the address in RI is incremented, okay, to point to, so now RI points to the next address in memory, okay? So something like this, it's going to go to the address that's stored at R2, get the number, and add it to R0, and then it's going to increment the address that's stored in R2, so now R2 points to the next address in memory. So it just does it automatically in a memory location. With this type of syntax, it's going to change RI to point to the next memory address, so the next time you use RI, it's already pointing to the next address, okay? And we have the auto decrement, which does the same thing, but it comes before, which means the effective address of your operand is the address that's in RI minus 4, okay? So it does this right away, and then gets the number at that new address, okay? And the reason that they do this after and this before is because it makes most sense for what we call a stack. And I think I mentioned a stack before. We're going to talk about memory stacks a lot more. Okay, so when we get there, if you look back to this, it'll be more obvious to you. Okay? All right, so we're done for today. We'll see you on Wednesday.